किसी स्टूडेंट का माइक ऑन है शायद.
Well, so good morning, everyone. So let us welcome our today's guest, Jithin BP, who has joined this session for us from Calicut, Kerala. He did his CS MS from Iser Mohali with thesis work on point contact spectroscopy and scanning tunneling microscopy. Interest in nuclear physics instrumentation, which was one of the topics in his PhD. He did his PhD from Central University, Himachal Pradesh, and did his postdoc on biosensing at University of Calicut, where he is affiliated now. Passionate researcher and a developer with a strong background in physics and a keen interest in robotics and embedded systems. His work focuses on creating practical hands-on solutions from academic research projects to founding a research-oriented company. He specializes in developing affordable data acquisition instruments and educational tools for nuclear physics and embedded systems. His area of expertise is with design and development, as well as bulk manufacturing for electronics. He has founded C-Spark Research for developing affordable data acquisition instruments for schools and colleges. And we have witnessed the class of the same to C-Lab 3.0. It's our privilege that Jithin is with us and will be telling the role of Python behind this wonderful game-changing device in school and college education. I welcome Jithin and I request him to start the session.
Thank you, sir. Can we just turn the camera towards the students? So, yeah, thank you. I'm happy to be here to introduce, in particular, the programmable nature of this device, where you have a Python library that allows you to access every function that this thing can execute. So without further ado, let me just spend about 5-10 minutes introducing the device. Sir has said that most of you have used this, but I'll just run through a few slides telling you what this is. So you have this device. So it's a collection of different test and measurement tools. So let's say you are studying electronics. There is a whole stack of equipment that you need. You need power supplies, you need waveform generators, voltmeters, capacitance, measurement resistance, oscilloscopes, so on and so forth. So it's a collection that is controlled via a connected device, such as your laptop or your Android phones. So this is a summary. Here you have all the features, and here you have the software side of things. So the hardware side of things interfaces with the real world, specializes in accurate data measurement, time-specific measurements, etc. And on the software side of things, on your computer, you can visualize nice plots, you can do fast analysis, etc. And of course, it is extensible through many add-on sensors that use the I2C or SPI communication interfaces. All sorts of things, everything from heartbeat, temperature, pressure, humidity, a lot of things. And I'm sure you're all already familiar with the software. So you have, this is the oscilloscope, and this is the Android app. And there are, of course, with this many experiments that you can do. Here you have a diode clamping circuit shown, for example. It just uses one diode and a capacitor. You need a sine wave that goes to the input and a DC that you can adjust to see the clamping behavior, how you can shift this waveform up and down. And this is the screenshots from the Android app, where you have many experiments. But we'll be focusing on the desktop side of things because we're going to look at programming with Python. So here you have, again, a lot of experiments like this. Now, These are, of course, some of the things you may have already done, for example, diode IV, and some more complex things, like, for example, filter characteristics. So here you have a waveform generator and the oscilloscope studying a filter circuit, frequency response curves. This is a list of all the sensors that, for example, if you're working on a particular project that involves measurement of UV, so you would select ML85 voltage output. Now you can measure voltage with CLAB, so therefore you'll be able to measure via this sensor the UV intensity in a room. So similarly, there is an entire whole list of sensors that you can purchase from various vendors online. They're all very affordable, like 100, 200, 300 rupees range. So this, I'm not sure if you have performed this. This is measurement of time of flight. So it's a setup that measures the time taken for this ball to fall through this distance, and you verify your S is equal to half AT square formula and calculate G, or conversely calculate S if G is known as 980 centimeters per second square. Now, this is, I'm not sure if many of you are familiar with this. This is like these demos circuit. You combine these blocks together. And for those of you who already know basic programming, there is this loop here where a variable set V goes from 0 to 4 volts in steps of 0.1. And then you set that voltage to PV1. And then you measure the voltage on A1, which is the voltage across the diode. And current is, of course, PV1 minus A1 by 1K using this sort of ammeter setup. So set V minus dV divided by 1000, that's your current. So X versus Y will actually give you these results. So this is very quick and easy to use, and mostly it's focused at very young kids who find it difficult to, look at syntax like this, typed code, that is. Various things that have been done with this: a simple heartbeat monitor using an LED and a phototransistor, using a sensor. This again costs 150 rupees. A little robot that's controlled with your phone. Cyclic voltammetry. This is some chemistry. Filter characteristics, PID controllers, etc. So okay, so let me just end the slides now. These are some community contributions. For example, thermoelectric measurements. Dr. Ujjwal Nikam has made this. You require data, and if you can automate data collection, you have a ton of data, and you can make nice plots, etc., and monitored it with CLAB. So as the instrument was taking measurements, I could see that, okay, there is a voltage that climbs and drops, and that's proportional to the amount of glucose present in the blood sample that was inserted. There's a simulator built in, which also I'll show you. And of course, every instrument is calibrated, every input, every output, all that is a calibration plot for one particular instrument. I don't know which one, but every one of these has a unique calibration plot, and that's stored in the device. So whenever you connect the device, these coefficients are loaded, and that's how you get accurate readings. Okay, so this is right. So now I shall get back to this. Okay, sorry. This. Okay. So right. So now let's come to the Python programming part of things. The video. Yeah. Sir, can you unmute and just confirm that the slides went well? Like.
Everyone is muted from host end, so that we can avoid echoes, right?
No, just mute.
And we can have some interaction. So all of them are following.
Okay, the slides went fine, right? Right now you are seeing the C Lab photo, but slides were okay, right?
Yeah, yeah.
Okay.
Slides
So
are
now, yeah. Now I'll go to the interface and just start with the Python sort of things. Okay. So now you're all familiar with this oscilloscope interface right here. Okay. So this is the software. And what I've done in the hardware is simply I have taken a wire and I have connected it to the sine wave generator, which gives you a sine wave here. So because you're all, you all have used this already, I'm not going into too much detail because we have to go quickly to the Python side of things. So here you have controls of the sine wave. I can adjust the frequency of the sine wave, and I can also click here and set the exact value for the sine wave that I want. Let's say I want 2 kilohertz, I can set it to 2 kilohertz. And at the bottom here, you have sine fitting. So this will tell me, okay, the amplitude is this much, the fit value is this much, etc. And there are 4 channels here. And you can do further analysis. For example, on the left here, you have Fourier transformation. So if I select FFT, you can get like this. So there is one sharp peak at 2 kilohertz. There you go. Okay. So this is the interface. Now let's go to the coding side of things. So here, second. Yeah. We just connect the device.
So this section is with app or desktop software.
This is on the desktop. We're focusing only on desktop right now.
Okay.
So I will just briefly introduce Python and I'll also show you the visual coding part of things. And yeah. So see, you were here at oscilloscope before. This menu is compressed. So there is write code, okay, in the right section. So this is where you can practice writing code. I'm not saying you should write all your code here, but here you can practice writing code. So on the left side, this is called an IPython console, interactive Python, where it says here, access hardware using the instance P. So it's already connected for you. When I write these 2 lines, first import EYES from the library called EYES17, and you open a device and you store it as the instance P. So now P has all the functions. So when I say dot and then I press tab, this will give you all the functions that are available here. Okay. So let's say get voltage, open the bracket. So now it tells you, okay, you have to enter the channel name. So let's say A1 and I say enter. So this is measuring the values from A1 and giving me. So you have different values because A1 is connected to a sine wave, which goes from -3 volts to 3 volts. So you will get random values. Now let me just change the connections, connect it to PV1. Okay. So now I should get a constant voltage. See, minus. So it's that the last third digit is, of course, small amount of noise, but it is near 0. Now let's say I want to set PV1 to a particular value. Okay. So set PV1 is the function. Let's say I want to set it to 1 volts. So now this is set to 1 volts. When I read it, now you get the same 1.00, 0.9997. So it is 1 volt within a few millivolts of error only. Okay. So there are many function calls. So now, of course, you can't just guess what function is available. You need proper documentation. So proper documentation is here. So if you go to the website for C Lab, you have this, and here you have different links here. So there are docs at SciSchool. There is a PDF brochure, technical specifications, and docs. So since you're programming, you need to click this, and that will take you to this page. So this gives you all the instructions, like for example, how to install. So let's say if you're on Windows, install EYES17lib using pip. So this is the function. If you're on Linux, this is how you install the library. Okay. So this is installation, and here Python functions, introduction. So this is all well documented here. For example, how do I connect these two lines, right? So it says this is connected. How do I read a voltage, which I just showed you? eyes.open print p.get voltage A1. Will print on the screen what is the measured voltage, sorted into analog voltage measurements. So this includes all these functions mentioned on the right. So everything from get voltage to oscilloscope functions. For example, capture one. So capture one is a function where the first parameter is channel, whether you want to measure A1, A2, A3, any of these analog channels. NS is number of samples. TG is the time gap in microsecond units. And this will give you X comma Y, which you can simply plot. So let's go back and let's just try a small capture function and see how that works. Okay. So I have here, let me reconnect the sine wave because I want to capture sine wave. And let's say P dot set sine 1000 hertz. So it has set 1000 hertz. Now, if I do get voltage, again, I'm getting random values. But if I do capture, P dot capture 1 from A1, how many samples do I? Let's say I want 1000 readings in 5 millisecond intervals, 5 microsecond intervals. So this will give me two arrays, which I need to store. So let me just say X or T comma V is equal to this. Okay, so now the moment I run this, T has now become an array of time data points. So it's equally spaced 1000 points from 0 to 5 milliseconds. And V is voltage readings. But of course, so much data makes no sense. So what I should do is import matplotlib or from matplotlib import pyplot. Let's just rename it as something else, PLT. So PLT is a plotting library now, okay, which is part of matplotlib. And plt.plot t comma v are two variables. Okay, these are two arrays. Now plot.show. So you see, I have programmatically obtained 1000 data points with intervals of I think 5 microseconds. So that gives me a total of 5 milliseconds, and therefore you have these many waves here. Okay, so this is, with few lines of code, which I can of course write here as one section. There is, if you go here, load example script, there is capture one, load. So see, to get an oscilloscope trace, all you need to do is first import the library, connect to the device, import the plotting library, capture 1000 points with 10 microsecond intervals, plot and show. That's it. So now when I say run script, will get plot. Correct? So that's it. This is all that is required. Now, instead of this, if I say put only 1 microsecond gap and get 1000, because it's a 1 kilohertz sine wave, you will get only one waveform. See, one full wave. Okay, little more. Say 2. Yeah. So what happened there was you could not take one microsecond. It scaled it up to 1.5. That's the minimum that you can do. You cannot put very small gaps. Okay. So there are many well-documented functions, all the functions that you find in this. So everything from, let's say, voltage outputs. So if I want to set PV1 or PV2, there is a function call here. Similarly, set PV2. So if you want to do a diode clipping experiment, you can do it like this. The code is here. You just have to make the clipping circuit on this on your breadboard, and you can interface it. Any questions on how to do this? Like, it will be clear only when you do it by hand, you sit in front of a computer and do it. But are there any queries?
1 minute.
Yes, sir.
Students are not known to Python programming. They'll be learning this in coming semesters. So can you please explain one of the program with respect to
Okay.
Python today?
You mean the software programs, like the ones that they're using here? See, if they are new to Python, we have to start from the basics of Python itself, right? So, okay. So like they're not familiar with Python at all, is what you're saying? Like you have not started writing programs.
Yes.
Okay, so in that case, I think we should start with visual programming first, and then we'll get to syntax, because visual programming gives you an idea of the logical flow in programming languages. So let me turn on visual programming. Okay. So when you go to the device menu and turn on visual programming, it says server is running, device is connected, open visual editor. There's a button here. Okay. So I'm going to open visual editor, which will take you to your browser here. So here, okay. And there is some program already sitting here. Let me just show you briefly some programming workflows. These things are drag and droppable. Okay. You can drag and close them like this. So let's start with the basics of what is a program. So what is the definition of a program? It's a set of instructions that a computer executes sequentially. So let's see how we can create these instructions. For example, on the left side, you have all these menus here. Let's take in/out. Print. Print is usually not for printing on paper, it's for showing on the screen. What is going to be printed? Let's take some value. Okay, so I want to print some text, attach the value here, hello world. Okay, so this is the program. Okay, just one instruction, print this on the screen. And when I run this, what do you see here on the bottom? Hello world. Okay, so now if I want to, I'm just going to quickly jump through, okay, programming concepts. If I want to print this 20 times, what can you do? You can duplicate this, keep attaching this 20 times, right? And right now, see, 3 have come, so you can do this 20 times. But that's not how you write programs. You can use something called loops. So here, there are loops. So repeat 20 times. You put this instruction inside the loop. So now, this has appeared 20 times. Now let's take it another step forward. Let's say you want to print numbers 1, 2, 3, 4, 5, 6, 7 up to 20. So now this simple loop cannot work. You cannot just write 1 here. You need something that changes. So for that, you have another type of loop, which is called count with step from 1 to 20 in steps of 1. So it'll go 1, 2, 3, 4, 5, 6 up to 20. What will go? This variable called step. So now if you go here to variables, so a variable is like a bucket. Okay, some value can be stored inside it. The name of the bucket is called step. The value that is initially stored is 1. Once it runs once, the value that is stored is 2, so on. So if you keep checking the value of the bucket, with every loop it changes in steps of 1. So go to variables here, take step, connect it here, and run. So you got 1, 6, 7, 8 up to 20. It's that simple. You can do the same in Python, but I'm just showing you programming concepts here. Okay, so let me just bring you guys here. Yeah. Now, how will you make a multiplication table with this? Let's say I want to make a multiplication table of the number 23. कैसे करोगे? Okay, so we need to multiply step with 23, right? For each step, go to take an operator, connect it here, step into 23. So what will happen? Step is first 1, step into 1, sorry, 1 into 23, 23 will come. Then it will become 2, 2 into 23, so 46 will come, so on and so forth. So let me run this. What will you see? 23, 46, 69, 92, 115, so on. So we have made a multiplication table. Now let's say, let's try and make a plot. So now instead of printing, let's go to plots. So plot x comma y. Let me make a parabola. How will you make a parabola? The formula of a parabola is y-axis is, y is equal to ax square, right? So let me take my mathematical operator here. Step into step. So y is step square and x is only step, right? So we will get 1 1, then we get 2 4, 3 9, so on. So now when I plot this, what did I get? I got 1/2 of a parabola. I want the left side half also. So what will I do? I go from minus 20 to 20, correct? I got my parabola. Now if I want a bigger parabola, I can just change the ranges, minus 100 to 100, and just run this. So now it has made a big parabola. So this is what programming is about. You should be able to automate the tasks, and there's a lot of things that you can do. For example, you want to do data collection over a long time, you can use this, or you can use Python. Of course, Python is faster, more efficient, but this is more, if you're a beginner, this is more friendly. Okay, so now what will happen if I just exchange these two? The parabola which looks like a U will now look like a C, right? Correct? So now we have seen what are variables, we have seen what are values, what are operators, logical conditions. If something is true, do this. If not, do something else. So these are all things that you will learn when you learn programming. Input and output, of course, printing, saving, etc. is there. We have different types of loops. We have mathematical operators like square roots, sine, trigonometry, all this is there. You have list. List is basically a collection of variables, different values stored in the same bucket, which you can access one by one. We have different types of plots, functions. Now coming to the stuff that deals with CLab. So there are different functions that deal with CLab. So let me make a diode IV experiment, show you how you can do diode IV with Python code, then show you how you can do diode IV with visual programming. Okay, and all these programs, this entire software is all open source, and you can find this in this repository, ExpEYES programs. I'll send you the links. I'll send Sir the links he can forward. So ExpEYES 17 code is here. So there's a lot of code that is involved, but we're going to look at simpler code sections. As a demo, I'll just show you, for example, if you were using the oscilloscope, in the bottom right section, okay, you have this edit code button. So when you say edit code, this entire code for the oscilloscope is actually visible to you, and you can also make changes to it, provided you understand it enough. So it's not hidden. You can make the changes. Like for example, if I think that this trace is not thick enough, I want to make it thicker, and I understand where that is written, I can just go here, find out where the traces are being made. So that's somewhere here. Pen colors, the colors are set here, and there is somewhere the width is mentioned. So I just need to change that width. So pen colors, background, high contrast pens. Okay. Yeah, see here there is width set to 2.3. Okay, and I can just simply change it, make it 5.3, and just run it again, and the width will change. Okay, so things like this are possible. Of course, you can copy this entire thing and run it on your setup also. So now let's go to diode IV. So start with the school level diode IV. Okay, so diode IV plot in the school level menu. So here, let me switch to screen share view. Yeah. So here the schematic is there, how to connect. So let me just make the connections, PV1 to breadboard. and then you take a diode and a resistor 1K. So I need to check whether the resistance is 1K. So let me just check that first in the oscilloscope and pick out a 1K resistor. Connect between. Here you see resistance has appeared. Okay, you're not able to see, 1 second. So here, when I connect between sun and ground, resistance has appeared here, 1.003K. So I know this is 1K. So now I've connected 1K. I will take one diode, which I'm not sure works, but let's see. Okay. Okay, going back to school level diode IV. And next step is, second. Yeah. So the next step is you need to connect the diode and two wires. So one end of the diode goes to ground. And the midpoint measures the diode's voltage using A1. Okay. So now that this is done, I'll show you this. Yeah. So the connections are made. Now what will happen as I increase PV1? So as I increase PV1, what do you see? A1 is following PV1. Okay. So why is that happening? Because whatever voltage you set here will appear here unless the diode conducts it, right? So the diode is not conducting. Whatever voltage I'm giving is appearing here. Let me increase this slowly by dragging this needle. I can also click in the center and set an exact value. Okay. If I want to set 0.5, I can set 0.5. Now, as I increase, see beyond 0.5, the diode's voltage is holding constant, right? It's not increasing much. Below that, see in the reverse section, still following, the voltage of the diode is tracking the applied voltage. But the moment it crosses what is called the knee voltage, the diode is conducting. So that voltage, A1 here, is now fairly constant. This is your IV plot, basically. This is what happens when you take the IV plot. So what you need to do is you need to use the spreadsheet that is provided to you. You put different voltages there. You measure, you take this reading, the voltage across the diode, put it here. You take the current, which is PV1 minus A1 by R1, which is calculated here. You put it here. Now you make set of readings. Okay, I'm not taking readings. I just show you how it works. Let's say 2, 2, whatever. You take 3, 5, and then you can just simply plot it, and you will get the plot. Okay, so if you take proper IV readings, you will get the IV curve. But I am a little lazy, so I'll just go to the automatic diode IV section, diode characteristics in the electronics menu. So now that I know that my diode IV works, I'll go to the electronics menu and diode characteristics and just start. So this will do that. Okay. So this is the IV plot for this diode. Now the same thing if I repeat with a red LED. Okay. So this is, I've replaced that diode with a red LED. Okay. And just start again. So this will now take IV curve for red. The moment it starts climbing, the color also is visible for the red LED. Okay. And if I take a blue LED, which has an even higher energy, therefore a higher band gap, therefore a higher knee voltage, this is your blue LED. So this way you have many different IV curves. Now, very recently, someone published a paper on IV characteristics and the temperature dependence of IV characteristics. So I'll show you what they did in a very crude manner, but just show that. Okay, so the IV is here. It's appearing properly, overlapping for this particular diode. Now, what we did there was we wanted to study the temperature dependence of the diode. Okay, so for that, I was a co-contributor, so I wrote a small code which is in the example scripts, and it's called IV3D. This is the code. Now, when I run this, this is plotting the diode's IV curves in 3D. It's just taking IV after IV after IV, okay? And it's just putting it there. So what do you observe here? We see that the band gap is same, right? Along the z-axis, they're all the same. They're all like exactly next to each other. But whether this plot will move to the left or to the right if I apply heat. Any answers? Sir is here.
Yes.
Yes, sir. So can anyone answer if I heat this diode with say I have a lighter or something? Yeah, I have a lighter.
Would like to see they can
What will happen to this IV curve? Will the
or you can even unmute and speak.
see what is heating? Heating is applying thermal energy, right? So the system has energy already, right, in the form of phonon modes, vibrations, right? Some energy is already there. So now, will it become easier to jump the band gap, or will it become more difficult?
Can this be called as 3D plot?
Yeah, it's plotted in 3D. In a sense, we have multiple IV curves that are appearing along the z-axis. It allows you to visualize any changes very easily. This was written for the paper. I'm just showing you that in Python it's very easy to make even fancy things like 3D this thing, and it looks nice in the paper. I'll also show you the paper, IOP Science. So okay, so it is paywalled, but this was the paper. It's I think 2 or 3 impact factor journal. But yeah, we don't have an answer yet. So should I just heat it and show you? Okay, so what I have here is I have a lighter, and I'm just going to heat this diode briefly. Try not to damage anything. So observe. What happened? Knee voltage went to the left.
Right.
It reduced. And now the diode is cooling. So it goes back to where it was before. Right?
Wonderful.
So this means you can use a diode as a thermometer. Once you create a calibration plot for the knee voltages, and you know that at this temperature this is the knee voltage, at this temperature this is the knee voltage, what you can do is you can simply use it as a thermometer. Put it in boiling water, see what happens to it. Put it in ice water, see what happens to it. Okay, so that is what the paper was about. They determined the temperature coefficient for the diode and used it as a thermometer. Okay, right. So the 3D view enables you to see very easily what happens when you make changes. So many different things like this are there. I think I can show you one more setup like this. Okay, so let me just close this. Okay, exit it. I'll go back to my oscilloscope view, and 1 second. Just connected. So let's say I want to look at half wave rectification. Okay, so all I need to do is flip this. Half wave, give a small load. Okay, so this is half wave rectified signal, correct? All I've done is I've used the sine wave, taken it through the diode, given it to A1. This is my half wave rectified signal. So here you have something called a 3D oscilloscope. Okay, so triggering, I need to work on triggering. So trigger level, yeah, slightly higher. So you see here also, it's just plotting the sine waves. Now here, what will happen if I heat it? You have done the half wave experiment, half wave rectifier experiment. Have you all done? So there, what
Yes.
happens is the rectified output is not overlapping the initial one. There is a small gap, and that gap comes because of the forward voltage. The diode needs a minimum of 0.5, 0.6 volts before it starts conducting. So that is subtracted. So if you give 3 volts, you only get something like 2.4 volt height. So here in this view, if I simply heat this diode, did you see that small bump? So यहाँ पे ऊपर हो गया. Now it's going back. Okay, so it will now loop back and overlap. So it's moving from right to left. I'll just give it a little heat. There you go. ऊपर गया, थोड़ा सा bump आया, and I'm going back. So these are many different things that you can study. Now let's get back to more experiments. Have you used sensors? Sir, have you used any sensors with this device? Or I'll show you a couple of sensors. Okay, so one sensor that I have here, this one. How many of you have used this sensor before? I think almost all of you have. This one, this tiny thing. Let me go to the sensors menu and activate it. Maybe one of you can guess that. So yeah, activated now. It's on. Have you seen this thing anywhere? Like, I don't know if you have. So basically, this is your pulse oximeter sensor, heart rate, and your oxygenation levels. So it's inside all those oximeters that you bought during COVID. So here, I have activated that sensor, and I'm going to put my finger on top of it, just gently. And how did I use this? Go to the sensors menu, go to I2C sensor data logger if you connect any sensor. This has detected this sensor, and now I'll just start measurements. Okay, and go to data logger. So this is measuring my heart rate. Okay, so it measures two traces, one with infrared light and the other with visible red light. And using these two, it determines the oxygenation levels. I'm not sure how, there is a formula to calculate, but what I'm just doing is I'm plotting the raw values. So I'm able to see my heartbeat on the screen. Okay, so this sensor is very cheap. It's about 120 rupees or something. And you can use it for heart rate measurements. Okay, so this way, there are many other sensors. So for example, this one, let me remove all these things. Is an accelerometer plus gyroscope. Okay, this is inside all your phones for measuring the tilt of the phone. So it's got connections VCC, ground, SCL, SDA. So VCC is 5 volts, ground, SCL, SDA is here. So you can just plug it in like this here. Now again, scan and detect. So this sensor has also been detected, MPU 6050. Start measurements. So here you have AX, AY, AZ. AX is 10 because downwards 9.8 meters per second. The other two are 0. So this also you can use for measuring, for example, pendulum. If you attach this to a pendulum, you can measure the frequency of the oscillations. So let me just pretend this is a pendulum and I'm just making it oscillate. See, so you can see the oscillations. Now, if I ask you what is the frequency of oscillations, how will you find out? You have the raw data points. All you need to do is just fit it. So I only need GZ, where the maximum rotations were happening, and say sine fit. So it has fitted this and tells me frequency is 2.327 hertz, frequency of oscillations. Okay. So using analysis tools, you can use all the data points to get a very accurate measurement of, so normally in school or college, if you want to find out the simple pendulum oscillations, what you do is you take 20 oscillations, divide by 20, try to get the correct thing. But here you just need even half an oscillation, you'll be able to get what is the frequency. Okay. Now I have a couple more experiments which I can show you. So here, for example, this is NPN transistors output characteristics. Have you done this experiment? You haven't. Okay. So electronics, NPN output characteristics. So here I can set different base currents and get the output characteristics. So 1.2, slightly higher base current. So here also, similar to diode IV, you can go and write programs for this. So for example, not sure if it's there, NPN transfer characteristics is there, or diode IV will be there. So okay. So diode IV is there. Let me show you diode IV first, because the code is already there. I don't have to write it. I will explain the code steps one by one. So the connections for diode IV should be same as before. Second. Okay, so I've made the connections for the diode IV. Let me just run this code and see if it gives me correct results. Okay, so it's working. Now, how did we get diode IV from this code? So how are we measuring diode IV? We have, let's look at the circuit here. We have PV1, an adjustable output voltage. We give it through a 1K resistor to a diode, and we measure the midpoint voltage here with A1, and the output of the diode goes to ground. Now we set different values for PV1 here, start from 0, 0.1, 0.2 up to let's say 5 volts. Then some voltage will be there measured by A1, which is basically voltage across the diode. So you get V. What is the current flowing through the diode? You can measure using this resistance, because the left side of the resistance is the applied voltage. The right side of the resistor is A1, which is what you measured. So PV1 minus A1 is the voltage across the resistance. Now using Ohm's law, current is equal to V by R. So V, PV1 minus A1 divided by R, this is 1K. So current, PV1 minus A1 by R. And the same current has to flow through this diode also. Kirchhoff's law. It cannot escape anywhere else. If it is going through this resistor, it also has to go through the diode. So now V and I both. So you just keep changing PV1 values in steps and you plot. So let's see what we have done here. In the software, is this visible? Is the text visible? Can you read it? Or should I make it bigger?
Please zoom the.
Okay, so let me just zoom this text thing. 1 second. Is this better?
Yes.
Okay. So now, what have we done here? First, we have imported this library. Very important. Import i17.eyes. Then we connect to it. So i17.eyes.open. You run this open function and store the results in P. So now P is the variable that contains all the functions that are used to access, measure, and control the CLAB device. Complete thing. And the entire thing is documented. Like I said, The entire documentation is here. Every function, if you go to the introduction section itself, you have all the functions for analog measurements, for digital outputs, waveforms, everything is here. Okay, so you can use this and go to the specific example. So function call summary is here. All these function calls are here. Okay, coming back here. Yeah. So now I have made two lists. Okay, store diode voltages here. So it will look like 0, 0.1, so on up to whatever voltage. Okay, so current, this also is a list of the current for each voltage. So we start with the starting voltage, let's say V is equal to 0.00. Now you give a while loop. So a while loop will loop everything inside the loop. So everything inside of the loop is with this indentation. So this entire block which is indented is part of this loop. So पहले हमने वो देखा था ना, the visual coding. So there you have this, it's physically placed inside the loop. So here you have indentation. In some languages you have brackets. Okay, so now while this condition is true, you keep running this loop. So is this condition true? Is V less than 5? Yes. So it will say VA is basically V applied, P dot set PV1 V. So you say set PV1, start with 0 volts. It will return the value that is actually set. Now, why are these two different? Because see, every output has a resolution. So if I say set 2 volts, it will maybe return 2 volts if it has managed to successfully set 4 volts. But if you ask it to, let's say, set 2.001 volts, so it will go to the nearest value that it can actually set, because it has a particular resolution, step size. Every instrument has a step size. So it will say, no, I was only able to set 2 volts, so it will return 2 volts. So even if you give some other arbitrary value that is outside the scope, it will tell you what is the value that was actually set. Now you need V diode. So that is of course measured. Get voltage from A1, which is the voltage across the diode, right? Now what is the current? Current is V applied minus V diode divided by 1K. But if you want current in milliamps,